Okay, good day. Welcome to the Mass Mathematical Domain. Today we are going to be looking at an interesting aspect of further maths for SS3 students. So we're looking at integral calculus. So here in this particular lecture, we'll be considering the introductory aspect of integral calculus. So lecture 1, introduction. Now, integral calculus is also known as integration. So another name for integral calculus is integration. Actually, calculus as a branch of mathematics is classified into two. Number one, we have differential calculus and we also have integral calculus. In this particular lecture, we are going to be looking at integral calculus. So integral calculus is also known as integration, and it is defined as the reverse process of differentiation. Note the word, reverse process of differentiation. It is often called antiderivative because it is the inverse of a derivative. Differentiation is called derivative. So integration is the antiderivative because it is always the inverse of a derivative. For instance, when we differentiate a function, if we differentiate a function, say y equals to f of x, now we simply start with an expression and then we proceed to find the derivative of this function. If I have a function y equals to f of x, to differentiate this function, I will say dy over dx is equals to what? F prime of x. Please take notes, for you to understand integration, you need to have a foundation on differentiation because integration is simply the reverse process of differentiation. So if I have a function y equals to f of x, I now differentiate the function dy over dx equals to f prime of x. So now, this f prime of x is called the derivative of the function f of x. But when we integrate, we simply start with this and go back to its original form. Differentiation is coming this way. Integration is using the answer and going back to its original form. So see, now you see, from f of x, original function given to us, if we differentiate it, we have f prime of x. Then if we integrate f prime of x, we come back to f of x. I think this is a better explanation to what integration is. Now let's consider some examples to illustrate what we have just said. If you have a function, let's say f of x, a function f of x equals to x raised to power of 6. Once you differentiate this function, you're going to have f prime of x equals to, remember our rule of differentiation, that if y equals to x raised to power of n, then dy over dx is equals to nx raised to power of n minus 1. So if f of x now being a function is equals to x raised to power of 6, then the differentiation f prime of x will give us 6x raised to power of 5. I hope you understand that. So if f of x is this, then f prime of x, which is also known as dy over dx, is what? 6x raised to power of 5. Therefore, it means that the integral of this 6x raised to power of 5 with respect to x will give us what? x6. Why? Because it is when we differentiated x6 that we got what? 6x5. It means that when we integrate 6x raised to power of 5, we are going to have what? X raised to power of 6. According to the above definition, that integration is the reverse process of differentiation. Now, I want you to note that the integral of 6x raised to the power of 5 from what we just illustrated here is written as this. So this sign is what we use to denote integral. The integral of 6x raised to power 5 is this elongated s, 6x raised to power 5 dx. I'm going to explain these symbols to you as we advance. So the symbol integral f prime of x dx denotes the integral of f prime of x with respect to the variable x. Take note of that. Now, this symbol for integral was developed from a capital letter S, which was used in the 17th century when the idea of calculus were first devised. Now, the expression under the integral sign f prime of x, like now I have integral f prime of x dx. This expression under the integral sign is called the integrand. So it is the expression to be integrated, and it is always referred to as what? The integrand. And this sign here, called with respect to x, is called the differential, and it is always there to assist in the evaluation of the integral. Now I want you to note something. The integral sign is just like a bracket that is open. So dx is like a closure of the bracket, meaning that for every integral sign there must always be a differential. You must tell us what you are integrating with respect to. So now let's interpret this. So integral f prime of x dx, this sign is called the integral sign. This, which is under the expression under the integral sign, is called the integrand, and this dx is called what? The differential, or you call it the integral assistance. I hope you understand that. Now let's establish some concepts. This concept is very important as it will help us in understanding the concept of constant in integrations. Please, I want you to pay attention. If f of x is equals to x raised to the power of 6, this is a function given, and I differentiate this function f prime of x, what I'm going to have is what? 6x raised to the power of 5. It therefore means that if I integrate this 6x raised to the power of 5 with respect to the x, what I'm going to have is what? X raised to the power of 6. Because integration is the reverse process of differentiation. Now let's look at case 2. Please take note of this case 1. In case 2, if I have a function f of x equals to x raised to the power of 6 plus 2. Now if I differentiate this function f prime of x, what I'm going to have is 6x raised to the power of 5 plus 0. Remember, the differentiation of a constant is what? 0. So what I'm going to be left with is what? 6x raised to the power of 5. Now, if I integrate this one, remember it was from here to here I got this answer through differentiation process. So if I integrate this, I'm going to have what? The same thing that was given to me. So integral of 6x raised to the power of 5 dx is given as x raised to the power of 6 plus 2, because it was from here I got to this one. I want you to note something very important. When I differentiated x raised to the power of 6, I got 6x raised to the power of 5. When I differentiated x raised to the power of 6 plus 2, I got 6x raised to the power of 5. Now, when I integrated 6x raised to the power of 5 for the first case, I had x raised to the power of 6. But when I integrated this one, I had x raised to the power of 6 plus 2. There's something I want you to note there. The same expression, but when integrated, I have different answers. Now, let's look at this case 3. If you have f of x equals to x raised to the power of 6 minus 20. If I differentiate this, I'm going to still have 6x raised to the power of 5. Of course, differentiation of a constant is 0. So this will give me 0. Now, so 6x raised to the power of 5 minus 0 is what? 6x raised to the power of 5. Now, in this case 3, the integral of 6x raised to the power of 5 dx will give me what? X raised to the power of 6 minus 20. Please look at something. We integrated 6x raised to the power of 5. In the first case, we had x raised to the power of 6. We integrated 6x raised to the power of 5. In the second case, we had x raised to the power of 6 plus 2. In the third case, we integrated 6x raised to the power of 5, and we had x raised to the power of 6 minus 20. That means in this first case, it is actually x raised to the power of 6 plus 0, because that was the original function given. Now, why do we have different answers like this? This function here was given and we got this as the answer. This function here plus 2 was given, we got the same answer. This function here was given and we got the same answer. What is the reason to this? Now, let's proceed while I explain in the next page. Now, I said that from the above 3 examples, since we know the expression from which the derivative 6x raised to the power of 5 was derived, so it was easier for us to find the integration. Like now, we knew the original function here was x raised to the power of 6. So when we got the answer, to integrate it, we just say the answer is x raised to the power of 6. Here, we knew the original function. When we integrated it, we got 6x raised to the power of 5. Sorry, when we differentiated this, we got this. Meaning that when we integrate this, we still got this one back. It was easier for us to actually know what the integration value is because we already knew the original problem. But it is crucial to note that once we took the derivative of the above 3 functions, all the constant terms that were there were 0. Like this one, the constant term here became 0. This minus 20, the constant term here become what? 0. So if we do not know the original expression, whose derivative is 6x raised to the power of 5, so we will not have any evidence of the value of the constant term. For instance, I tell you, integrate 6x raised to the power of 5 dx. And now the answer equals to what? X raised to the power of what? 6. I don't know whether it is plus 2 or plus 3 or minus 10 or plus 50, because I don't know the original function that was used to get this answer. So for that reason, it is important to always acknowledge the presence of a constant term by adding a symbol C to the result of any integration process. Please, this is very important. It is important to always acknowledge the presence of a constant term by adding a symbol C to the result of any integration process. What we are simply saying here is that if you are integrating 6x raised to the power of 5 dx, the answer is what? X raised to the power of 6 plus C. C is a constant term. It may be 0, as in the first case here, C was 0. It may be 2, as in the second case here, C was 2. It may be minus 20, as in the third case here, C was minus 20. So please, whenever you are doing an integration problem, always remember to add a constant C to your answer. And this constant C can actually be determined if we know further information about the function. Like now you see, in case 1, the function we had was f of x equals to x raised to the power of 6 plus 0, right? Which on differentiation, we got 6x raised to the power of 5. Now when I integrated this answer, I got x raised to the power of 6 plus C. So it means in the first case, our C is 0. Now, in the second case, the function we had was f of x equals to x raised to the power of 6 plus 2, which on differentiation, I got 6x raised to the power of 5. Now, when I integrate this 6x raised to the power of 5 dx, the answer I'm going to have is what? X raised to the power of 6 plus 2. Here, our c is equals to 2. You don't need to bother about the value of c. The value of c can only be determined if further information about the function is given to you. Now, in case 3, our function was f of x equals to x raised to the power of 6 minus 20, which on differentiation we got 6x raised to the power of 5. When we integrate 6x raised to the power of 5 dx, we got what? X raised to the power of 6 plus c. So in this case 3, our c was what? Minus 20. C is called the constant of integration and must always be included. Students, please take note of that. It must always be included. Now let's take this definition together. An integral with a constant of integration c added to it is called an indefinite integral. An integral with a constant of integration c added to it is called an indefinite integral, since we normally do not know the value of c. However, in certain circumstances, as I've explained earlier, the value of c might be found if further information about the integral is available. Now, I want us to look at some important concepts. If you have a differentiation, let's say, of course, originally you were given a function y equals to f of x. Please follow me, I want to derive something. If I differentiate this, dy over dx is equals to what? F prime of x. On cross multiplying, if I cross multiply this, I will have dy equals to f prime of x dx. Now, since the integration is the reverse of differentiation, now if I integrate both sides, so introducing the integral sign on both sides, which I could just simply say integrating both sides. Now, if I integrate both sides, I'm going to have integral of dy is equals to integral of f prime of x dx. Of course, since the integral is the reverse of differential, so this and this will go. So what I'm left with is y equals to integral of f prime of x dx. Now, if I assume, let's assume that f of x is equals to the integral of f prime of x dx. Then, when you replace this with this, we have y equals to what? F of x, the original function given. And I told you, for every integration, always add a constant of integration, which is plus c. Please, this is just an introductory lecture. We are trying to establish the fundamental concept of integrals. So what I've explained so far is what is here in this lecture introductory notes. And that's what we got here. You can see that the original function was this. When we differentiated it, we got this. When we integrated this, we got the solution back, which is the same thing here. And of course, with the constant of integration c. In this case, the c is what? 0. Okay, we have come to the end of this particular introductory lecture. In our next class, we are going to look at integral calculus lecture 2. Here we'll look at integration of x raised to the power of n. See you in our next class. Thank you for your attention.